Okay, good evening, everybody. This is lecture number 2. We're going to continue working on logic and proofs. So let me show you an outline for today, which I didn't put everything on there. I'm going to do a brief review of last time, and then we're going to do some more logical equivalences like we did last time. Don't worry if you don't remember what that is, because we're going to be going over that again. And we're also going to be doing logical implications later today. But first, let me go over the syllabus right quick. So we do have homework assignments in this class, tests, and computer tutorials. Homework assignments are going to be worth 30% of your grade. And there's 10 homework assignments. We're going to have 4 tests, and that's worth 60% of your grade. And we'll have 3 tutorials, and that's worth 10% of your grade. Briefly, let me explain how the tests are going to work. We will have 4 tests in the class. 3 of them will be during our lecture times, and the 4th one will be during the final exam time. It is not a comprehensive exam. But after you take test number 4, the second half of the exam time we'll use to do a makeup exam. So you can choose any one of tests 1 through 3 to do a makeup on, and during the second half of the final you'll take that makeup, and if you make a better score, that will replace the original score that you make on your test. So that gives you a chance to make up if you have a bad day, bad test day, or some material was a little hard for you the first time. If you learn it by the end of the class, you have a chance to show me that on one of the tests. If you take a look at your handout, let's see, on page 2, under course policies, which I'll put this right here. This is also on the website. Let's take a look at that. And what's important about this is I want to let you know what my expectations are. I expect you to participate in class, pay attention and do your homework and all of that good stuff. And homework assignments are due. I'll be giving you the due dates as soon as I give you the homeworks. And they will be accepted late with a 50% penalty. If you have special circumstances, you need to let me know, and we may work out no penalty if that's the case. If you miss a lot on your homework and you feel like you could have done a lot better, you may rework problems and resubmit your homeworks for up to half the credit back if you make below a 90. So if you make an 89 or below, you may resubmit your homework. If you make above a 90, I'm going to give you those points back automatically, because I'm going to assume that the errors you made are things like a plus sign or small clerical errors that it would waste my time to check and waste your time to rewrite and turn back in. The last important thing for me to mention is that I do have a guaranteed C option in this class, and typically that's very useful when I really have a huge class. That option is that if you do all of the homeworks and you turn in regrades until you get at least 70% of the questions right, you take all of the tests, you do all of the tutorials, and you have to take all of the makeup tests. Like at the final, there's 3 makeup tests, you only get to take 1, but you have to take all 3 if you need a guaranteed C. So if you do all of the coursework and you work an extra set of problems, which is called the special tests, then you will receive a guaranteed C in the class. And I'll go ahead and let you know that if you're trying to do all of that work, you're going to make at least a B in this class. Because basically you're going to be getting the grade for what you understand, and if you're doing all of the work, you will understand at least 80% of the material, so you should make a B. But if for some chance you don't do all of the work during the semester and you decide the last couple of weeks that, oh, I'd really like that guaranteed C, you'll be putting in a lot of hours, but eventually you'll understand it all, and you will deserve a C when you get one. Okay, so I just wanted to mention those course policies. All of these items are on the website, so you can take a look at that anytime you want to review. So let's do a review of the things that we talked about last time. So we talked about logic and proof. We started with the definition of a proposition. And that was a true-false statement. We represented that with a small letter P or Q. And we also said that true was equal to 1 and false was equal to 0. We made tables with that. And then to remind you of the operators we talked about negation. We used a symbol that's like a little corner of a square, and that stands for not. For conjunction, which is anding two statements together, we used an A with no bar in the middle. For disjunction, which is or, we used a little V. These are hard to remember, so that's why I was making a table for you. For implication, we used an arrow from P implies Q. For equivalence, we had a double arrow. For exclusive or, we had a plus with a circle around it. And for logical equivalence, we had a double arrow with 2 lines in the middle. So we'll go over some of those things again. Are there questions about these items? There was one little note I wanted to make. In your textbook, they don't use this operator here. They don't use an arrow for implies. They use a double arrow. We're going to have another meaning for a double arrow in this class, and I'm going to talk about that in a little while.
I think they don't use the not also, the symbol for the not in the textbook.
I believe in the last chapter they do, in chapter 9 on Boolean algebra, they'll probably use that symbol.
And do we have that symbol in the computer keyboard?
No. But since it's not, you could also use a minus sign. So if you wanted to type these things, you could use a minus sign for not. Okay, so at the end of class, we were talking about logical equivalences. And the one that we were talking about was the implication rule. That was the first one we derived. And that was that P implies Q is logically equivalent to not P or Q. Does everyone remember that? So what was one of the stories that went with implication?
I have a purple shirt and I have a Q on the shirt.
I have a purple shirt.
And I have a Q on
And
the
I have
shirt.
a Q on it. I was using that example for P and Q, P or Q.
I remember. It's the candy.
So we were using
The candy.
If the child behaves, he gets candy.
right. If the child is good, they're going to get some candy. All right. And so this statement was going to be false when the child was,
Good and doesn't get of candy.
if they were good and didn't get any candy. That was when they were going to throw a fit because mom broke her promise, right? Okay. So the only time that this statement is false is when P is true and Q is false. So this was our first logical equivalence that we proved, and it was called the implication rule. The next one comes from this equivalent definition is that the only time P implies Q is false is when P is true and Q is false. So let's prove that with the truth table. So first we'll put our values in for P and Q. So remember that we start with the 2 values of P are zeros, and then 2 1s, and Q is 0 1 0 1. Okay, and we'll make a column for P implies Q. That was true if P was false, and also whenever P is true and Q is true, and false otherwise. So if I negate that, I get a 0 in the first row, a 0 in the second row, a 1 in the third row, and a 0 in the last row. So what I'm doing is an element by element. So each row I'm negating the value that is in P implies Q. For the negation, I'm negating that value. So when I have 1 1 0 1, that opposite is going to have 3 zeros and 1 1. So remember that logical equivalence, we want to have all 1s. We want it to always be true. Okay, so we're going to check that last. That'll be the last thing that we check. So the next thing we'll do is we'll check P ANDed with not Q. So what is P ANDed with not Q here? If P is false, then P and not Q is?
P is false, not false.
If P is false, then P and not Q is false.
False.
So again, in the second row, P and not Q is going to be false. In the third row, we have P is true and Q is false. So P and not Q is
True.
true. In the last row, we have P is true and Q is true. So P and not Q
False.
is false, because not Q is 0 in that case. And so when I AND a 1 and a 0, I get a 0. So then we're going to compare this first column with the second column. So we're going to compare the quantity not P implies Q with P and not Q. How does that look quick down there? Okay, so the first column and the last column are the same. So row by row, we're going to get a 1 because these are equivalent. You can also make a visual proof of that by drawing little arrows for both sides. So are there any questions about that?
Yeah, got a question. The column under not.
The column under not,
Yeah. What does that represent? Not P or not Q? What is it?
when I do a proof with the truth table, I write the statement I'm proving in a line across the top,
Okay.
and then under each item I fill in the truth values.
Okay.
So this a not applies to P implies Q in this statement. So in the entire line, the not applies to P implies Q.
Yes.
So in this column, this not is the negation of the next column.
Oh, okay. Got you.
That's sort of a shorthand to help me be able to read the top and tell what I'm proving.
Yeah.
Technically,
so-
can you distribute that not sign through the P and the Q? So it'd be not P implies not Q?
That's a good question. Can we distribute the not inside the P implies Q? Would that be not P implies not Q? Well, first of all, let me pose that question to everyone. What does the rest of the class think?
It would probably change the operator as well.
It would probably change the operator. We're going to talk about a rule that shows us that it changes the operator in just a minute. But if we remember, P implies Q is like an OR, right? But we've just shown that not P implies Q is just like an AND. So if I were to change this, the implication is no longer going to be an implication because it's now equivalent to an AND, which has only one true value, and an implication always has 3 true values. So that's an easy way for me to say, no, I can't use a not of an implication is not another implication. That brings me to a rule I wanted to teach today. So let's do that.
I'll take my $10 later.
You'll take your $10 later, all right. So the rule we're going to do now is called De Morgan's rule. And De Morgan must have been a very smart guy working with logic, because he let us know what happens when we negate statements in logic. So if I take the statement P or Q, I believe that last time we talked about the fact that since OR has 3 true values in our truth table and has 1, then they're probably related by a negation. Because a negation of an OR is going to give me 1 true value, a negation of an AND is going to give me 3 true values. So there's probably a relationship there. Let's talk about what that is. So if we have P or Q, and then we negate that, De Morgan's rule tells me that's equivalent to negating P, changing the operator from an OR to an AND negating Q. So if we make a truth table for that, notice here I'm making a column for the not. So I'm going to
Gotcha.
fill out the P or Q, then I'll fill out the not for that. And then I'm also going to make columns over here for not P and not Q, so it'll be easier for us to do this AND. And then at the end, I'm going to compare column 1 with column 2. So let's fill out our values for P and Q, 0011, 0101. Then for P or Q, that was false in the first row and true in the rest, because OR is true when either P is true or Q is true. The negation of that will have a 1 in the first row and what in the rest?
0.
We'll have falses or zeros in the rest of the rows. Now, let's just fill out not P and not Q here to make sure we don't make mistakes on this AND statement. Not P is going to be 1, 1, 0, 0, the opposite of P. Not Q is going to be 1, 0, 1, 0. So our next step is to AND these two statements together. So in the first row, we have a 1 ANDed with a 1, which gives me
1.
a 1. In the second row, we have 1 and 0, which gives me
0.
0. In the third, I have 0 and 1, which gives me
0.
0. And in the last column, I have 0 ANDed with 0,
1.
which gives me a 0. Remember that AND is like multiplication. So if I have any zeros at all, my result is going to have a 0. And OR is the opposite. It's like plus. If I have any 1s at all, the OR is going to give me a 1. So now this logical equivalence is going to compare column 1 and column 2. We can just look at that and see if they are the same. Are they the same?
Yep.
Yes. So row by row, the values are the same. So our logical implication is true. By the way, if you try to do a proof and you try to fill out the column for logical implication and it doesn't come out with all 1s, then it's not a proof. It's only a proof if the statement's always true. So if we can negate OR with De Morgan's, do you think we could also negate an AND with De Morgan's?
Sure.
Sure, we sure can. So De Morgan did both of them. Didn't stop with just halfway. Did both ways. So if we have not the quantity P and Q, that's logically equivalent to, what do you think?
Not P or not Q.
Not P or not Q. Exactly right. What happens to this statement if I change all the P's into A's and all of the Q's into B's?
Same thing.
It's the same. What happens if I change all the P's into smiley faces and Q's into hearts?
Still the
Same thing.
Still the same. Still means the same thing. Okay. So the P's and the Q's are placeholders. Just like any function in mathematics, the letters that we use are placeholders and they're going to be true no matter what the statement happens to be. So the reason why I mentioned that is that we might have more complicated looking things where we'll still use De Morgan's rule and it will still be this basic rule. So instead of P, I might have something more complicated like A and B instead of P. ANDed with B implies C maybe. And then I might negate that whole thing. And using De Morgan's, that would be logically equivalent to negating the first variable, not the quantity A and B, changing the AND into a OR, and then doing what?
Negating the next.
Negating the second variable. So that would give me not B implies C. So you can see that using brackets and parentheses is going to be really important when you start to have more than two variables or more complicated combinations of variables. Are there questions about that? Does anyone need to see a De Morgan's truth table proof for this rule? Kind of believe it, right? Makes sense. Okay, so both of De Morgan's rules work the same. So anytime I see an AND or an OR with a not outside, I negate both of the variables and I switch the operator in between ANDs and ORs. Okay. So that's how we remember De Morgan's. Okay, we have some other rules that might seem really obvious, but let's go ahead and just state them. What would be the commutative rule? If I have P and Q, Does anyone know what commuting is?
Changing them around.
Changing the places. So commutative is going to say that P and Q is the same or logically equivalent to Q and P. So we do that in our heads automatically. Like if I see 2 plus 3, I know that's the same as 3 plus 2. Because addition and multiplication are commutative. Okay, so we also have the same thing with ORs. So P or Q is logically equivalent to Q or P.
That wouldn't work necessarily for like implication, would it?
It doesn't work for implication,
Right.
right? Because it really depended on the hypothesis and the conclusion, which one was true and which one was false, to tell me whether the statement was true. But since and is like multiplication, then it doesn't matter what order they are. Same thing for or. So if I have P implies Q, I can't just reverse the order of that. So that doesn't mean the same thing as Q implies P. You know, everyone knows this because we talked about P implies Q was something like, if you're good, I'm going to give you some candy, right? That's different than saying, if I give you candy, you're going to be good. Doesn't happen, right? Kid eats the candy and forgets. Okay, they may or may not be good after you give them the candy. Okay, so, but what happens, what do you think we could do to reverse the order of this?
Well, if it was equivalence, it would be commutative, right?
Yes. If P and Q had the same value, then it is commutative. So
No,
commutative works.
I was saying instead of implication, if it was equivalence
Right.
between the two operators.
Right, so P is equivalent to Q, is logically equivalent to Q is equivalent to P. So order doesn't matter for the equivalence operator, which is also if and only if. So this is basically a substitution. P is the same as Q is like a substitution. So let's talk about how we could reverse the order of an implication, because sometimes you'd like to know something about Q being the hypothesis instead of being the conclusion of an implication. So if I have P implies Q, if I tell you, if it rains, I'm going to get wet, then if I tell you I'm not wet, what do you know?
Didn't rain.
I know that it didn't rain. So if P implies Q is true, then not Q implies what?
Not P.
Not P. Okay, so let's use the implication rule that we derived in the first class to show us why this is true. So P implies Q is logically equivalent to not Q implies not P. And the name of this rule is contrapositive. So let's do a short little proof without truth tables, because truth table proofs get hairy, right? So let's use some of the rules that we've already derived to show that this is true. So when I do a formal proof, this is my first formal proof I'm going to introduce here. I write statements on the left. Then I write reasons on the right. And I make nice columns. And then I put line numbers. So then, during my proof, anytime I make a reference to something I said before that was true, I'll use the line number to refer to where I got my information from. So it's sort of primitive bibliography, okay, or citations while you're doing your proof. Okay, so if I start with P implies Q, and I want to end with not Q implies not P, so I'm going to use this as my given. So my reason is going to be that P implies Q is given. Now I want to prove that it's logically equivalent to not Q implies not P. So what was a logical equivalence that we knew about implication? It was the first one that we did. We talked about implication being the same as an or.
Not P or Q.
So P implies Q was the same as not P or Q. And what line number did I use there? I only have one choice. I used line number 1, knowing that P implies Q is true. And then I used the implication rule. And that was the one that told us that P implies Q was the same as not P or Q. Now, in order to change this back into an implication, I need to reverse the order of P and Q, right? Q has to come first. Right? So let's reverse the order. And that's going to use our commutative rule. Q or not P comes from line 2 and commutative. What's next?
Could you do sort of the reverse of what you did on line 2? Use implication?
Yes, ma'am. We sure can do the reverse of what we did on line 2, since it was a logical equivalence. Anytime we see an or, we can change it into an implication. So if we see an implication, we can change it to an or, but we can also go the other way. So since this is an or, we have to negate the first variable and make it imply the second one. So we get not Q, change the or into an implication, and then write down the second variable. And that was from line 3 and the implication rule used in the reverse direction. Ta-da!
Get that.
I know it's confusing. Next week I will be giving you a sheet that will have all of the rules, and I'm also going to post them on the website, so you'll be able to look up the implication rule and see how it works both ways. So just remember that the implication rule said if I have P implies Q, that's the same as saying not P or Q.
Okay.
So if I have an or statement, say A or B, if I use this rule going that way, if I notice here this variable, the opposite of this implies the other variable.
Okay.
So if I start with an or, then the opposite of the first one will imply the second one.
Okay.
So this is logically equivalent to saying not A implies B, using the rule backwards. So from going from right to left instead of left to right. Are there more questions about how we did that with the implication rule? So when we have a logical equivalence, it doesn't matter if we start with the left or if we start with the right, we have the same result because we can go both ways. So if the arrow doesn't go both ways, it tells you where you can start from and where you can go to. So that's our next thing after this. But let's just go back to this proof briefly. So here's a formal proof. Our first line was given, and our last line is what we wanted to prove. So once your last line has the statement that you are wishing to prove, you're done. You don't have to write anything further. So this is a proof using some other rules, using the implication rule and commutative of the contrapositive rule. So now once we've derived this, we can use the contrapositive rule from now on without having to convert our implication into an or and then commute and then change it back into an implication again. So we've done a shortcut. So we've saved ourselves the work of having to write a truth table and being able to use logic instead, being able to use a proof instead.
Question. Whenever you're making up proofs for, say, other theories that you may have, if you want to use the contrapositive rule, is it better form to just say the contrapositive rule, or do you actually have to go through and prove that the contrapositive rule is in effect?
That's a very good question. So the question was, if I'm trying to do a proof and I want to include a contrapositive rule, can I just say it's a contrapositive rule, or do I have to go over to the side and write a little proof? Basically, in logic, there's an accepted set of axioms. So there's an accepted set of rules, and contrapositive is one of them. So I'm going to give you a sheet that has the ones that I'll accept in proofs in this class, and those are the ones I'll expect you to use when you do proofs for this class. So if you were to do some other class that has a logic system, they'll give you a set of axioms that you're allowed to use, and then anything else that you want to use, you have to do a little proof on the side for. So if you want to make up your own rule, like if I wanted to have Tiffany's rule, I could make a truth table proof or a small formal proof like this for any rule I want to have, as long as it's true. and then I can call it Tiffany's rule from then on after I've done a proof. So when I was writing a formal proof, I could, on the right, I could write, that's one of my reasons I could write Tiffany's rule after I derived it and gave it a name. So that's one of the real reasons people go into mathematics, because they can name things after themselves without having to have a lot of money. So as you can see, implication is really important in our logic proofs. So let me put this proof back up here, because I want to mention something that I didn't mention when I first mentioned a formal proof. In general, when we're doing formal proofs, we're not proving logical equivalences. This one happens to be a logical equivalence, but we didn't prove both ways. Every step we used was a logical equivalence, so we can go backwards. We could go from the bottom back up to the top, since every step was a logical equivalence. But since I didn't say on there that that's what I was doing, this proof is an accepted way. Writing the givens and then deriving the proof statement is an accepted way to prove a logical implication, which means that I can assume that this is, if I assume this is true, then this must be true. So if the given is true, then what I proved must be true, but it doesn't necessarily go the other way, because I could use rules that only go one way for my reasons. But since all of my reasons were logical equivalences, I can go back and do another proof that starts with line 4 and goes up to line 1. And that would prove both directions. So this proof actually really only proves that P implies Q logically implies not Q implies not P. So the reason why these kinds of proof works is that a formal proof is a list of true things. So you assume that one thing is true, and then you derive true things from that. Assuming that the first part is true, then everything you derive in the proof has to be true. And you can't put anything that's false in there. Okay, so let me just write that. A formal proof is a list of true statements which leads from the given to the conclusion. So I've just shown you a direct proof. That has the first line as the given, and the last line is what you wanted to prove. So the last line has the conclusion. So in a proof, for each line to be true and to be correct in a proof, I need to have the statement that I'm trying to make. I have to have references to any line numbers I use, and I have to have a reason for every single one. All the axioms that I'm going to give you are going to use at most 2 line numbers. So if you write a line that refers to lines 1, 2, 3, 4, and 5, I'm going to mark it wrong, because I already know that you didn't use the rule the right way, because you're only allowed to combine 2 lines at a time. Are there questions about that? So why do you think I mentioned that this was a direct proof? Because there's also indirect proofs. Okay. I wouldn't have mentioned it otherwise. Actually, before I go on, let me mention one thing about this. If a formal proof is a list of true statements which leads from the given to the conclusion, do you think it's useful to write down every single thing that's true from the givens?
Maybe before you do the proof, but not.
You might want to make a list over on the side of things that you knew, over on the side of things that you knew were true before you start the proof. But in the proof, you don't want to put a lot of extra things, right? So just because I know that the moon is not made of green cheese doesn't mean I'm going to put that in a proof. Okay, so if I'm trying to prove that, if it rains, I'm going to get wet, I'm going to write things about rain and getting wet and nothing about anything else. And I'm also not going to just reverse orders of variables just for no reason either. So when you do a proof, I'm going to teach you how to be directed when you do your proof. So you can be directed in direct proofs and also in indirect proofs. But in each case, I want you to make sure that you're working towards some goal and not just floundering around and writing down things that you know are true using all the lines, all the axioms that I'm going to give you for doing proofs. Several of the axioms are in Chapter 9, by the way. The ones that we're talking about today, they're all in Chapter 9, except for the implication rule. So indirect proof. So formal proofs prove that P implies Q with a logical implication. So that means that anytime P is true,
Move it down a little bit.
oh, sorry. Then Q must be true. So how is this different from writing just P implies Q where the implication sign has just one line? This symbol is different because sometimes this one can be false. Right? P implies Q can be false, but P logically implies Q always has to be true, no matter what P is. Okay, so this is what I write when I know that P implies Q is always true. This is what I write when I'm not sure whether P implies Q or not. Okay, so one thing that we've talked about several times is an example of P implies Q. If I know that P is true, then what do I know? If P implies Q is true, and P is true, then I know Q is true. But it doesn't go both ways, right? If I know Q is true, it doesn't tell me anything about P implies Q or P. So that is our very first logical implication. So if I know P implies Q, and I know P, that logically implies Q. So in formal proofs, I'm going to do a logical implication proof that if I assume P, then I'm going to eventually end up with Q in the proof, which means that it must be true if P was true in the beginning. Okay, so this is just like saying, if it rains, I'll get wet, and saying that it's raining, I can conclude that I'm getting wet. So this is another way to write this rule, is to put the true lines stacked on top of each other and then put the conclusion after drawing a line. That's another way to write a rule, if it's easier to see that way for you. And this rule is called modus ponens. You're going to hate the Latin names for these things. So I'll write it again on another slide. So the two ways to write this are one-line statement, or also to just write both of the statements, and you don't have to draw the and on the left. It's just to draw a line underneath both of those statements and to write down the conclusion at the end. You can put a therefore symbol if you like, which has 3 dots that make a triangle. That means therefore. The reason why it's nice to see the rule this way is because when I'm doing a formal proof, sometimes I'll have P on one line, and I'll have P implies Q on another line, and then I can easily look at this rule and go, oh, I can write Q on the next line, using these 2 lines above. Okay, so say that this were in a proof, if that was line 1 and line 2, and these were both given, then this would be line 3, and it would refer to lines 1 and 2 and use the modus ponens rule, which I'll write as MP. Questions about that? So in a proof, I can use modus ponens, but as soon as I use that, that means I can't do the proof backwards, right? I can't go from the conclusion and go back up to the hypothesis. So as soon as I use a rule like this, I can't go both ways. So our goal in doing this is to figure out how to write proofs, because you'll be given some givens and things to prove from those givens, and you'll need to be able to write formal proofs and do truth table proofs. You want to do both of them. Be able to fill out truth tables and to write proofs. And why do you think it's useful to write proofs like this? Do you think a computer can do these things if I give it the axioms?
Yes.
Yes. That's why it's good to be able to write proofs like this, because if I ever want to build any kind of artificial intelligence, then I'm going to need a way of representing knowledge and a way of getting from things that I know to things I didn't know yet, right? So this is an example of going from things that I know to things I didn't already know. So this is an example where I say, well, it's raining outside, and someone told me that if it rains, I'm going to get wet, then I know I'm getting wet. Because the computer doesn't necessarily have skin that tells it that it's getting wet, right? But it can build a logic system that will tell it that it's getting wet based on knowledge that it already has. So that's why it's very important to do this. And it also is very important to do this because if we want to do things like prove that our program is correct, no matter what input we have, I might want to say, well, I know that it's true in the very first case where I run my algorithm, right? If I plug in 0, my input is 0, then it's true, right? And then I might say, well, if n is true, then I can prove that n plus 1 is going to be true. If I show that I could do that, then I could prove it for any number, right? As long as I prove it for my first case and that I can go from any case to the next one, then that proves it for any number that I want to put in. So that actually goes to another method of proof we're going to use later, which is called induction. So induction is based on this modus ponens right here, and that's why this is a really important rule. Because all of our systems of logic and reasoning come from this basic definition of implication and definition of modus ponens.
How complicated does it get when you add, let's say, a third variable or a third of P, Q, and R?
P, Q, and an R.
Into the algorithm that you are trying to prove or disprove.
Well, if I were using a truth table, it doubles the complexity, right? Because if I have 2 variables with 2 values each, then I have 4 rows in my truth table, right? If I have 3 variables with 2 values each, then how many rows do I have?
8.
I have 8. So it doubles the complexity for that. But in terms of doing logic proofs, the nice thing is it doesn't really double it. Because since we're dealing with, places where the variables are, and just using double operators that deal with only 2 variables at a time or 2 combinations of variables at a time, then it doesn't really make it much more complicated if we're going to do a formal proof like this. So let's do an example like that. So let's say that we're given that P implies Q, R implies S, and I know not Q or R. Sorry, I'm making this up as we go. Okay, so these are going to be my givens. And at the top, I'm going to write what I want to prove. I want to prove that P implies S. Okay, we're going to use a rule I haven't derived yet, but it's going to be one that you'll understand immediately. Okay? So first, let me mention that when we're doing a formal proof, excuse me, when we do a formal proof, a lot of times when we want to combine lines, we want them to look the same. So if I have implications, lots of implications, and I have some ors, I'm going to change the ors into implications, just in the hopes that I'll be able to combine them in a nice way. Okay? So that's a hint. Whenever you're doing a proof, changing ors into implications is often a good idea. So let's go ahead and do that. So if I change not Q or R into an implication, what do I get? I have to negate the first variable, which gives me Q, change the or into an implication, and then write down the second one. So that was from line 3 and the implication rule. So the reason for doing line 4 was that I wanted it to look similar to the other lines in the proof so that I could use them together. Now, when I'm going to do this direct proof, what I'm going to do is I'm going to look at the statement that I'm trying to prove, which is P implies S. First, I'm going to look for something that looks like that. So if I see anything in the proof that looks remotely like it, I'm going to go for that. So what's the first thing that we see that looks like P implies S? R implies S looks like it, but I'd probably look for the P implies something first.
P implies.
But that's good. That looks like it too. So P implies Q looks a lot like it. So if we could magically change that Q into an S, we'd be very happy, right?
Yeah.
Okay? So I know that I want to use line 1 and combine it with something else that will get rid of that Q.
Implies S.
So I have Q implies R here. So the only other line I have is with a Q on it is line 4. So I'm hoping that there's a rule that combines lines 1 and 4 and magically gets rid of the Q. And I'm not going to worry about the R yet. I just want to do one thing at a time. So does anyone have an idea of what that rule might be?
Can you substitute one
Something to do with equivalent.
Yeah.
So we want a rule that says what? We want a rule that says if P implies Q and Q implies R, then what?
P implies R.
Right, so we want a rule that says P implies Q and Q implies R logically implies P implies R. So let's make sure first that this makes sense. We'd like to have this rule, but we want to make sure first that it's a rule that would maybe be one of our axioms. Okay, so let's translate it into English. So P implies Q, let's say that if it rains, I'm going to get wet. And so Q is getting wet, right? So I would need, the second statement should be, if I get wet, then I'm going to catch a cold, or something like that, right? And immediately, because you know English and because you use reasoning all the time, you already know that if it rains, you're going to catch a cold, right? So this is a rule that makes sense. All of the rules that we have should be things that make sense to you logically. And this rule is called hypothetical syllogism. And there's another name for it. It's also called transitivity of implication. It's good to know both of these names because we're going to talk about transitivity much later in the class, sort of towards the end, the 8th week of 8th homework, we'll be doing stuff with transitive. So transitive is a property that less than or equal to has. So if 3 is less than 5 and 5 is less than 7, then I know that 3 is less than 7. And actually, that reminds me that we had operators for and, right? We said that was like multiply, right? Mm-hmm. We said or was like plus. Implication is like less than. If you look at your truth table, and I'd like you to do that tonight after you leave class, look at your truth table and see, is P implies Q the same as P is less than Q? So I'm not sure about that. Well, I'm sure about that, but I want you to make sure. Okay? So less than and implication are equivalent operators. So I want you to check it with a truth table later. So and less than is transitive, so is implication. So we're going to use our hypothetical syllogism rule, combining lines 1 and 4. So on 5, we're going to write P implies R. And we use lines 1 and 4 and our lovely new rule, hypothetical syllogism, which I'm going to abbreviate. And it is all right for you to abbreviate these things on your homework. And now that we've gotten a new rule, we're going to get really happy with this one. Okay? So now we have P implies R, and we're still trying to prove P implies S. So now we want to get rid of that R. So what do you think we'll do to get rid of R?
You do 5 and 2.
So we can combine 5 and 2 to get P implies S. Because we have P implies R and R implies S, so we can skip over the middle variable and get P implies S using lines 2 and 5 and hypothetical syllogism again. So as you can see, it doesn't make our proof a whole lot more complex. It just means that we have to look a little harder for where our variables are. But we still use the same kinds of rules, and we still combine only 2 lines at a time. Are there questions about this? Let's take the last few minutes and talk about indirect proofs. Okay? So the main method of indirect proof is called proof by contradiction. And you see this a lot in a math class, in like lots of regular math classes, like calculus or something, instead of logic classes. So indirect proof, there are 2 methods. One is proof by contradiction. And the second is proof by contrapositive. So we just did a direct proof. A direct proof is characterized by having the given at the beginning and ending up with the conclusion. Indirect proof is going to start with our givens if we have proof by contradiction, and it's going to end with a contradiction. So first I have to tell you what a contradiction is. Does anyone know what a contradiction is?
The negation of the conclusion.
We are going to use a negation of the conclusion, but what does contradiction itself mean? So just in regular English, what does contradiction mean?
Yeah, it means you double spoke. You said one thing, but it really meant another.
Yeah.
So a contradiction is something that is always false,
Yes.
right? So if I tell you that I'm going to give you $10, and then later I tell you I'm not going to give you any money ever, then you say, hey, one of those things you said must be false, right? Because the statement you just made, those are opposites. So if I add those together, it comes out with a contradiction. Okay, so we'll write that down in logic terms. A contradiction is P and not P is logically equivalent to 0. And this is called contradiction rule. So if I and P with its opposite, that's always false. And that makes sense. If I tell you I have red hair and I tell you I don't have red hair, then one of those is false. The statement, I have red hair and I don't have red hair, is false by definition. Because we know that each statement is a proposition that has either a true or false value. So it can't be true that P and not P are both true at the same time. Okay. So analogously, we could use De Morgan's on this. Let's do that. Let's negate both sides. Since we have a logical equivalence, then both sides are equal, right? So if I negate both sides, that should still be equal,
Yeah.
right? So let's do that. If I negate both sides, I get not P and not P is logically equivalent to not 0. And what is not 0?
0.
It's 1. The opposite of 0 is 1. So remember that not is like opposite. So not 0 is going to give me 1. And De Morgan's told me that if I have an and, then I negate the first variable, change the and to an or, and negate the second variable. So using De Morgan's, I get not P or not P. So that was the De Morgan's rule.
Which is P. Not P is P, right?
Right. Not P is P, and that's another rule that I didn't mention the name of.
Double negative.
It's called double negation. So not P or P is logically equivalent to 1. I can just copy the rest, and that was by the double negation rule, which says that not P is logically equivalent to P. So we just derived another rule. This rule is called tautology. Because tautology is something that is always true. So P or not P is a statement that's always true. I either have red hair or I don't have red hair is always true. So as you can see, these two rules are equivalent. I can derive one from the other using De Morgan's. Because since both of these are logical equivalences, I can also derive starting with the bottom line and going up to the top. So proof by contradiction is going to involve having a contradiction in my proof. So let's go back to that, unless there are some questions about this. Does anyone have questions about this? All of these rules that we've been talking about today will be on your axiom list that I'll be giving out next week and also posting on the website.
Question. Will we be expected to have that list during exam time, or are we supposed to remember them?
The question was, are you expected to bring that list with you? No, I will always give you the list.
Oh.
Anytime you have an exam that has proofs on it, you'll always be given the list. I have copies of them that I just keep and give out during exams. So you'll have your own copy to use for your homework, and we'll give you another one during the test. So all the tests are closed book, closed note. And so we'll give you any materials that you need while you're in the test. Okay, so let's go back to proof by contradiction. If you remember at the beginning of class, we talked about implication rule. And we said P implies Q. We actually said that the opposite of that was logically equivalent to P and not Q. Right? Because P implies Q was false whenever P was true and Q was false. So we did that at the beginning. So if we negate both sides of this, we can get P implies Q. I did a double negation and skipped writing that down. So if I negate both sides, I get P implies Q is logically equivalent to not the quantity P and not Q. Okay, so the reason for that was negating both sides. So remember that I said in a formal proof, we're going to prove a statement. We'll start with P, and then we'll derive Q. If we do a proof by contradiction, we're going to assume P and not Q, and then show that we have that that's false. Okay, and this is kind of confusing, so I'm going to explain it in a few different ways. Okay. So in proof by contradiction, assume we're proving P logically implies Q. So in proof by contradiction, we assume P and we assume not Q and show that this is impossible. So your mom probably used this on you when you were a kid. Okay? So suppose your mom came home and there's a broken window. My mother did this. There's 3 kids. She has 3 kids and we were home by ourselves. Okay? There was a broken window. There were 3 kids and a broken window. She was like, "Who broke the window?" And I said, "I didn't do it." And my brother said, "I didn't do it." And my sister said, "I didn't do it." And she goes, 3 children. Was there anyone else here? No. Who broke the window? Something had to be false, right? So that existence of that broken window means that somebody lied. So that's what we're going to do is we're going to derive that something is false and then go back and say that something that we started with must have been false, right? So somebody lied. So what we're going to do is we're going to assume these 2 things and derive a false and then say somebody lied, but we know that P is true because that was a given, so it must be that this was false, right? So the lie must have been not Q. So if that's a lie, then what's true? Q must have been true. So that's another way to show that P logically implies Q. is if we start with P and not Q, show that that gives a false, then the lie must have happened with Q, so P implies Q must be true. So it's kind of like convoluted, but you'll get used to it. This method of proof is really, really useful, particularly when you're not doing logic proofs, like if you're doing proofs with numbers. Like, say you wanted to prove that the square root of 2 was irrational. A rational number is a ratio of two integers, and I wanted to prove that the square root of 2 is not rational. The only way to prove it would be to list all of the combinations of integers and dividing them and showing that none of them was the square root of 2. That would be a direct proof. Who wants to do that one? Raise your hand. Anybody? No. Much rather do proof by contradiction, where I can say, assume that square root of 2 is rational, and then try to figure out something that is false after that. Right? So if I could figure out something was false, then I could say, well, it must be irrational. And that's a lot easier to do, although the logic seems a little confusing. But when you get used to it, it's really, really useful. So let's go back to the proof that we did earlier and see if we can do it with proof by contradiction. So here was our proof. So the difference is, what we're going to do is we're going to start with our givens, just like that. And we'll write them on a new sheet, because you can see right through them. I'm proving P implies S. So the very first thing I do in a proof by contradiction is I write down the negation of the conclusion. I have to write down the opposite of what I'm trying to prove. So that goes on line 4. I write not, put parentheses, and copy down what I'm trying to prove, and I give my reason as negation of conclusion. And this is something you're always going to do if you're doing proof by contradiction. A lot of times in this class, I'm going to give you methods for doing things, and there's going to be parts of it that I want you to do without thinking. This is one of them. Because if you think, you might try to do a negation in your head, and then you might introduce an error into your proof before you even get started. So I want you to write the line number, write a not, put parentheses, put the thing that you're trying to prove, put another in parentheses, and write negation of the conclusion. Because if you don't skip steps, you probably won't make mistakes. It's when we try to do stuff in our heads, even me, it's when I try to do stuff in my head, that's when I make the mistakes. If everything is written on the paper, you can even go back and see where the mistake was. If you do something in your head, there's no chalkboard to look back at. You already erased it. Okay? So now we have to figure out what to do with this. So we already said that we can't use negation on implication, right? We can't just change it into another implication. We have to do something else. We did say that not the quantity P implies Q was the same as what? P and not Q. We could use that rule if we want to, or we can use the implication rule that we already remember really well, which is that P implies Q is the same as not P or Q. And I like to do that myself because I only like to remember as few things as I possibly can. Okay? So what I'm going to do is I'm going to use my implication rule on here because I know I can't distribute a not unless I have an or an and. So I'm going to change this implication into an or by negating the first variable, changing the implication into an or, and copying down the second variable. So that was from line 4, and implication. Let me make one note. We just used a logical equivalence. So logical equivalences are always true no matter what, right? So I said that anytime I have an implication, that's the same as an or, where I negate the first variable and or it with the second variable. But logical implications aren't that way, right? So I can't take inside a not, I can't do a substitution with the logical implication rule. I'm going to talk about that more later, but I wanted to mention it right now. The thing I just did, you cannot do, say, with modus ponens or hypothetical syllogism. I can't just go inside a not and say that I have P and P implies Q and put Q in there using modus ponens, because the whole statement is negated, so none of that stuff in there might be true. Okay? But logical equivalences are like substitution. I can do it any time. Okay, now I can do De Morgan's. So if I do De Morgan's on line 5, then I negate, since I have a not on the outside, I negate both variables and change the or into an and. So let's be a little bit of a stickler right now. I'm going to go ahead and just act like the computer and write a not sign in front of the first variable, not P, and not S is what I get if I use De Morgan's on line 5. On your homeworks, when you prove that, turn this in, I don't mind if you put P right here. But I want you to know that you did skip a step, which is double negation, that tells you that not P is the same as P. So that was from line 6. I used a double negation to tell me that. So again, let me mention that I don't mind you using double negation in your head on the proofs, because not is something that we naturally understand that makes it true. It changes it back into, not P changes it back into P. But technically, a computer's going to need to do this. So if a computer was doing a proof, it would have to do both of these steps. Okay, so what we're going to do in proof by contradiction is first we write down the negation and the conclusion. Then we try to do De Morgan's on it. The next thing we do after that, and this is what I like about proof by contradiction, is I want to do simplification on this. Do you remember that when we talked about and, we said that if we knew an and was true, that gave us lots of information, right? Because if I said I knew that P and Q was true, then P must be true and Q must be true, right? So here I know that P and not S is true, so I can write that P is true, right? So let's write that on line 8. P is true from 7 and simplification. That's the name of the rule that tells me if I have an and, then I can simplify it to each of the variables that got anded together. So I can also write not S from line 7 and simplification. And in the direct proof, we were looking at what we were trying to prove, and we were constantly trying to make something look like that. But remember, in a proof by contradiction, we're trying to get a false at the end. So all I'm trying to do is get one variable and find another one that it's the exact opposite, because then I can put them together and get a 0, right? Because I had P and not P always gives me false, and that's what I'm looking for. Doesn't matter if it's P, could be smiley faces, right? Smile and not smile gives me false. Okay, so I'm just looking for two things and they're opposite. So the method is write down the negation, the conclusion, do De Morgan's, and simplification. That's what we're going to do. And then this is what I call my money. These are the things that I got from my negation, the conclusion. So we did all of these steps just to get this money. Okay, and this is the store. We're going to go spend our money at the store. Okay, the givens are our store. And the things that we derive from the negation and the conclusion are our money. Now, if I do a lot of things that combine things from our store, from the givens, but not from the negation and the conclusion, do you think I can get a false?
Say that again.
If I don't use anything below step 4, and I just combined lines 1, 2, and 3, and I kept just combining them, do you think I can get a false line in my proof? I shouldn't be able to, because I assumed that everything in the givens was true.
Yeah.
So I shouldn't be able to get a false out of those. My false should come from the negation and conclusion. Remember that was the lie. So the false has to come from there. So I need to use the things from the negation and conclusion and use them in combination with the givens to get a false. So that's why it makes a lot of sense to take the negation and conclusion and break it into pieces and then recombine those pieces back with the top. So let's try that. What can we buy with a P?
P implies Q, so you can get a Q.
So if P implies Q and I have P, then I know Q is true. That was my modus ponens rule. So that was from lines 1 and 8 and modus ponens. So we sort of used this money, so I'm just going to kind of mark it so I know I used that money. Okay, this is helping me figure out what I've already used and what I haven't used. Okay, so Q, I could go back and this becomes new money. Okay, so I can go back and see what can I buy with Q. We already used line 1. The only thing with a Q on it is line 3. Line 3 says, I either have an apple or I have an orange. Line 10 says the opposite of having an apple, right? So line 10 says I don't have an apple, so what must be true? I must have an orange. So lines 2 and 10 can combine, and the rule is disjunctive syllogism. So if I combine lines, sorry, did I say 2 and 10? It's 3 and 10. 3 and 10 combine to give me R. So if I say either I have an apple or an orange, and I tell you I don't have an apple, then I must have an orange. That's how I remember this rule, is the apple-orange rule. Okay, and I'm going to write it on its own sheet for you. Just for a second. If I have an apple, or an orange, that's kind of a flat one, and I don't have an apple, that means I have an orange. And this is called disjunctive syllogism. The reason why it's called that is because disjunction stands for or. That's what or is disjunction. And disjunctive syllogism is using a disjunction and combining some lines and deriving something else that's true. So hypothetical syllogism was using a hypothesis and combining some things to derive something else was true. So that's the apple-orange rule. So now we've already used our Q money, line 10, so 11 is our new money. So we don't forget that we still have some money in line 9. Okay, so we're still looking for something and its opposite. I don't see any opposites yet, so I'm still working. Okay, so now I'm going to use my R money. What do I get with R money?
Yes.
I get S money from line 2. So 2 and 11 and modus ponens, MP, I'm going to abbreviate that, is going to give me S. And lo and behold, my new money, S, if I look back up at the other money that I have, line 9, S and not S are opposites, right? So let me write those together just so any skeptics will know that I see S and not S are opposites. I'm going to put them together on the same line. That's going to be called conjunction because I'm going to and two things together in my proof. A formal proof is a list of things that are all true at the same time, so there's actually automatically a little and in between every line. So anytime I want to combine two lines, I can. I can do a little and. So I can put this and on the line by itself. The very last thing I do in a proof by contradiction is to say that something anded with its opposite is false. So that's what I do. On line 14, I'm going to write 0, and I'm going to say line 13 and the contradiction rule. And when I end a proof with that, I know that I've just proved the thing that I wanted to prove. So we just have about 30 seconds left. So let me just mention the things that we did today. We talked briefly again about truth table proofs. We talked about formal proofs. And we did direct and indirect methods. We just did proof by contradiction, and that's the only one you need to do in this class. You can use the other one, and I'll talk about that briefly next class. Next class, I'll also give you a handout with the axioms and probably your first homework assignment also. Next week, your proof tutorial is going to be ready as well. So if you want to go ahead and download the portal program, which will help you log on and do the tutorials, you can go ahead and do that. Or if you don't have a computer with internet access at home, you may also contact me and we can set up an appointment for you to use the computers in my office. I have 5 computers available for people to use. If you want to come in and take the tutorials there, you're very welcome to. Thank you, and I'll see you next time.